we're going to need a new and bigger array. So we're going to have two different options that we're going to need to go for, right? We can consider creating an array that is bigger than the old one by a fixed amount. So in other words, our length is going to grow by some constant c. Our old array was 15 elements, and we're going to add 5 more elements, right? And then our old array was 20 elements, and once again, we're going to add 5 more elements, and then 25 plus 5, and so on and so forth, into perpetuity. So that's one option, and this is called arithmetic or incremental growth. Okay. Option number 2 is that we create an array that's a proportional amount bigger. So we're always multiplying it by some proportion. So if we go and our old array is 15, the first time we might increase it by 5, right? Multiply it by 1.33, right? So we're going to increase it by a third. So that's going to be 20. Well, the next time we're going to do the same thing, and we're going to increase it by, let's say, 6. And then we're going to do it again, and this is going to increase it by 7. You can see how every time we expand our array under this paradigm, it's growing. But not only is it growing, the amount that it's growing by is growing. So these are the different approaches that you can have. This is called geometric growth. Okay, these are the two approaches. Which do we think is going to be better? We have 4 votes for geometric. Why? We have a vote for it sounds more cool, which is not terribly useful. We have one that says that as the array gets big, 5 really doesn't do a whole lot, which is true. We have a question basically of if you choose arithmetic, but it still needs more space than the fixed size, that's why geometric is better. And then we have one that says that it will be faster for increasing the size. And that is the crux. So let's go through one by one, and let's take a look at, and hopefully we can get through these two. Let's take a look at arithmetic growth versus geometric growth. We're going to look at an analysis of each. So I hope you guys brought your math hats today, because it's going to get mathy in here. So we're going to start with arithmetic growth. We got to start here, okay? First of all, we're gonna analyze it with respect to memory. You think it's going to be good with memory or bad compared to geometric growth? Yeah, good. Worst case scenarios, we're going to have C minus 1 empty slots, right? If C is our constant that we're increasing by, if we increase by 5 because our array is full, after the growth, we're only going to have 4 empty slots. So we're going to be pretty efficient with respect to memory. Run times where things get a little tricky. So for this explanation, we are going to assume that we start with an empty array, an empty underlying array, okay? No elements in it. And we're going to assume that our C is our constant that our array grows by, 5 or 15 or whatever that number is. It's some unknown constant, okay? Then we can do some quick math and we can go, okay, we're going to grow this array n times because we're going to have n elements in it. So we're not going to grow it n times. We're going to grow it some unknown value, right? We're going to have n elements put in. And if we divide that by the number of elements that we grow each time, we can get another constant, k, right? N over C, 1,000 divided by 5, we're going to have 200 resizes, right? Can we see what k is representing? Do we understand why this is what it is? Okay. I got 3 yes, 4 yes. I'll take that. That's basically a quorum. Cool. So now we're going to count ish the number of operations. Remember, we don't have to be perfectly precise if we're using big O notation. We have to get the general class correct, but the exact number of each quantification can be a little off, okay? Having said that, we know we are going to call n add operations in total because we're going to add n elements, right? So we can see how this works. We on board so far? Cool. So when we expand, right, out of our initial array, we're not going to have to do anything. But then when we expand the second time, well, it says the first resize. Really, the first resize after we've added elements in it, right? We're going to have C elements in it. So if we've got 5 elements in the array, we're going to have to copy those 5 elements over to the new array of size 10. So we are going to have C copy actions. But then when we expand again, we're going to have 2C additional copy actions. You know, when we go from 10 to 15, we're going to have to copy the 10 elements over so that we've got an array of 15 with 10 filled elements. We following? We see how this is being constructed? Cool. Where is this going to stop? How many copies are we going to have at the end? Right, we're going to do 1 times C, then 2 times C. How far do you think we're going to go? We can be more specific than pretty far. How many times are we going to expand our array? Right? Yeah, 200 in the example I gave, but specifically under this equation, we're going to do it k times. Right? Because k times C, right, is n over C times C is n. So we can see that we're going to do C plus 2C plus 3C all the way up to plus KC. Okay, this is the general equation. This is pretty gnarly. So let's see if we can reduce this. Let's see if we can make some sense out of this nonsense. So the first thing we want to do is we want to group our like terms together, right? We got a bunch of factors here that have C in common. So let's do that. We're going to group them together, and then we can pull the C out. Everyone with me? Okay. Now, I don't know how much those of us in the room like maths, as the British say, right? Because that makes more sense, mathematics, but math. Yeah. So, if you sum a sequence of integers starting at 1 and go to some value, right? If you add them all up, then that equals that maximum value times the value minus 1 divided by 2. That is the equation, right? Sum all the numbers from 1 to 5. Well, 5 plus 4, right? Right, 5 plus 4 is 9. What am I doing wrong there? I did something wrong. What did I do wrong? 1 plus 2 plus 3 plus 4 plus 5, 9, 12, 15. Oh, I see what I did wrong. It's the other way. It's plus. It's plus, not minus. Right? This equals 15. Add 1 to it, it's 21. Well, 6 times 7 is 42. So my equation is wrong. Not by much. So I will fix that in post. We'll leave it as is for now. You'll see when we expand this out that this doesn't matter, that minor issue really doesn't matter, right? So we're going up to K. So we're going to have this, right? We need to expand this out though. So this is going to become K squared plus K over 2, right? So we can then take that and turn that into CK squared, 1/2 CK squared, plus 1/2 CK. Do we all see how we get from this slightly altered equation to this? Okay. So if we then plop that back into our equation, as n gets infinitely large, which of these two matter more? The CK squared or the CK? Right. And do we care about the half? From a big O perspective, right? So we don't care about the half, so that can go away. And if these two are the two elements that we need to concern ourselves about, K squared is going to matter more than K. So really, we're only worried about this CK squared term, which is why that plus doesn't matter. It can be plus, it can be minus. It really doesn't matter because we care about this portion of the term, not this portion. So if we take this equation and put it in big O notation, we get to this, n plus CK squared. Does this tell us anything yet? Like, do you guys feel like, oh, that makes sense? This is going to run in n plus ck squared time. Do you have a good feel for what that means? You guys are better than me. I wouldn't. I'd look at this and go, I don't know. Hey, can we substitute for k? What's k again? N over c, but you have the right idea, right? Yeah. So we can do that. We can substitute. We can go, hey, let's put that back in there. Let's see where we can get. Right? C is a constant. C is some number. C is 12 or 5 or whatever. We don't know what it is, but we know it's a constant. Well, if we do this, right, one of these C's cancels out with one of these C's, and we get this. So what is that going to simplify to in terms of big O notation? Do we care about this term or this term? We have votes for the right term, right? This doesn't matter. Do we care about the C? No. So we can simplify this to big O of n squared, okay? This is the analysis of the runtime of all append, add, whatever you use, all insert and growth operations across all n insertions. Okay, this is the sum total. So now we can do a little more math and we can say, okay, well, we did n calls. So on average, big O of n squared over n, we can say on average, each operation is a linear operation. Some of these are going to be constant, some of these are going to be linear. But on average, each operation is going to be linear. Do we feel okay about this? Do we have a decent gut feel for how that works? Good.